I entitled this lesson, Solving Circuits. You can solve any circuit with two rules. There's one called a current law and one called a voltage law. What are the current laws? They break them into two subparts. First of all, current in a circuit flows downhill. It flows from the positive part of a terminal to the negative part of a terminal. That's current. Yep. Did you guys get notes? I missed you guys? Good gosh. Current flows, I said, downhill from positive to negative. In fact, if you ask me to look at a circuit, if I get a circuit schematic, one of the first things I'll do is I'll go find where the battery is. Remember the battery symbol? And if not, we'll talk about that again. And I say, which is the positive part? And I draw a little arrow saying that way is downhill. That is opposite from what happens in real life. In real life, it's electrons that move. In real life, electrons move from negative to positive. But I said to you, it's so much nicer to think of stuff moving downhill, going from positive to negative, that we define current as which way the positives would move if they could, even though they don't, because they're stuck in the nucleus. So current flows downhill from positive to negative. And the second rule of current is at any junction, any place where two wires join, current flowing in equals current flowing out. I've been using a ski hill analogy. I've said that every single circuit was sort of like a ski hill. I said the battery, the voltage source, is like the chairlift. It lifts you up the mountain. How do you get back down the mountain? Well, in skiing, you have to go down hills. In a circuit, you must go through resistors. And you've got to get back down to ground level before you can get back on the chairlift, before you can get back into the battery. So in terms of my ski hill analogy, CL, the current law means that if three skiers converge on an intersection, three skiers leave. In my picture here, Sherry, we're saying if I have 2 amps flowing to the right and 1 amp flowing up and they meet right here, how many amps must be going out of that meeting? Do the math. If I have 2 amps coming in here and 1 amp coming in here, how many amps must end up going this way? 3 amps. And often you'll find you can add that part in your head. The calculator stuff is going to be for some of the other things. Current in equals current out. That's the current law. Current in a circuit does not vanish. So example 1 says, find the unknown currents. Let me zoom in a little bit. Okay. Where's the battery in this circuit? Which of those is the battery symbol? Top, bottom, right, or left? Okay, left. There's the battery. That's the voltage source. Which part is positive? The top part of the battery or the bottom part of the battery? William. Okay, long, bigger, positive, short. Okay, so let's put a little plus right there. And what that means, William, is current flows this way. That's downhill. I always just add that right away, and I'm going to ski downhill. William, do you ski? Let's go snowboarding. Ready? William, how many amps, how many skiers right here? Just read. What does it say? Now, keep skiing, keep skiing. Everybody goes down this hill because there's no other wires going other directions. Everyone goes down this hill. How many amps right here? Skiers can't vanish. Current can't vanish. How many amps must be right there? If you measured the amperage right there, what would it say? You're right, Mohammed. What? 1.75. This is the current rule. If in this circuit you also measured the current at the bottom right here, do you know how many amps you would measure? 1.75. If I'm solving a circuit, generally if I know total current, the rest of the circuit's going to fall apart. In fact, in Physics 12, I teach all of my, we're doing this unit right now. In fact, their test is on Tuesday, and Jared, all of them know, oh, first thing I look for is total current. What do I mean by total current? How many skiers, how many amps are leaving the chairlift? How many amps are leaving the battery? How many amps are leaving the battery? Oh, right there, because there was no junctions, no wires breaking off, no forks in the path. Everything went right there. Let's try a trickier one. Where's the battery, first of all? On the left. Which way is downhill? up the page. Let's draw a little arrow like that. Adrian, do you ski? Let's go snowboarding. Okay. I'm going to say ski from just, I don't want to have to always distinguish, but skiing or snowboarding, the physics is the analogy still works. So here's my chairlift. This is where we start. I wonder how many skiers, how many amps are in this circuit? How many skiers are on this hill? Well, how many amps right here? 3 amps. That, because there was no junctions, here's a junction right here, but there was no junctions between the chairlift and right there, that must be how many skiers, how many amps came off the chairlift. That must be. Okay? Okay? Mohammed, Deb, put that away. Work on that later. Okay? I'll give you time later if I can. So, how many amps right here? Yes. Why? Because that's how many amps are right there and they haven't had a chance to break off anywhere. So you know what? Let's write that. I always add the current leaving the chairlift. Let's go skiing. Right here we come to a fork in the ski hill. Some skiers went down. How many amps went down? How many amps must have gone to the right if we started out with 3 amps? How many amps must have gone to the right? 2.2. Is that okay? 2.2 amps went this way. 2.2 amps, because there's still my 3 amps. You see it, Micah? 2.2 amps went this way. 2.2 amps went this way, Adrian. 2.2 amps went this way. Adrian, how many amps are right here? Must be. And what direction are they skiing right there? What direction is downhill, to the left or to the right? This, by the way, this is why we decided it's much easier to think of current moving downhill. To try and do this all backwards up is just confusing. Oh, here's the 0.8, here's the 2.2. They meet up right there. So how many amps are right where I drew that dot? Deb, face the front.
3.
So how many amps right here? Yep. What direction? Think about it. Yep. That's the current law. All I can do is give you more forks and more junctions, but it's, hey, start on the chairlift, carefully work your way through, and as long as you ski carefully, you can probably figure out how many amps are in each location. Yep.
When we have the test, will we check your 8 amp and 9 amp?
I'll be combining them both. Yep. Let's try another one. A little tougher. It says, show the direction of each current and then find the unknown currents. Hey, where's the battery? The voltage source on the left. Which way is downhill? Let's do that. Do I know how many amps total in this current? In this circuit? Do I know how many skiers? Well, they didn't tell me how many skiers here like they did on the previous one, but this is downhill. Oh, here's a junction. How many amps went that way? How many amps went that way? How many amps must have been right there for that to occur? Huh? So how many amps are leaving the chairlift in the first place? How many amps are leaving the battery in the first place? Must be 13 amps. That's how many skiers are on the hill. Now the analogy breaks down because I'm going to have decimals and you really can't have 0.8 of a skier, but we'll still go with it. So we got 13 amps worth of skiers here. And 8 of them went down, leaving how much? 5. Oh, here's another junction. How many went this way, Sinead? How many must have gone to the right then? You're right. What? 3. Question, Deb? Where's my seating plan? Where's my seating plan? Okay. Does it hit everybody? Thank you, dear. Okay. Put that away temporarily, though, right, Deb? With me here? Oh, and by the way, what direction are these skiers right here going? Are they going to the right or to the left? Which way is downhill for them?
Right.
To the right. Let's put a little arrow there, just reminding ourselves that's downhill. Hey, this resistor right here, how many amps of current must be going through that resistor? 3. I'll just write that even though I didn't ask for it. How many amps are sitting right here?
3.
Must be. I knew you guys could handle this. Which way? Right there.
Left.
Left. down, left, they meet up. How many amps right where I drew this dot? 5, moving which way? So how many amps am I going to fill in at the bottom here? 5 amps, moving which way? Left. Oh, and how many amps are going to be at the very, very bottom here? Careful. Back to 13. What we're really saying is, in a circuit, Jared, electrons can't vanish. But rather than look at electrons because they're so small, we look at amps current because that's a much bigger number. It lets us talk. Electrons have a charge of like 1 trillionth. We'll use current. Easy to do the math in our head that way. Let's try another one. Evan, you want to go skiing? Let's go skiing. Where's the battery? No. Where's the battery? Come on. Bottom. Which way is downhill from that battery on the bottom? Yep. Let's go a little thunk downhill. As I ski through, I really want to find, the first thing I want to try and find is how many amps are in this hill grand total. Now, I noticed they split up here. If they told me all 3 of those, I could just add them all up because that would be all of the skiers. Did they tell me all 3? Nope. They meet up again. What? I heard some. Jared, what? You know what? Right there, since there was no junctions from here to here, like all the skiers must go through that resistor, that's the total current. They snuck it in, but they snuck it in further down. So how many amps are in this circuit grand total? Let's put that leaving the chairlift right here. And I'm telling you, once you know total current, once you know how many amps are leaving your battery, Rebecca, the question falls apart. Evan, let's go skiing. That's downhill. Some went this way, some went that way, some went that way. Can you figure out how many went in this right-hand one? How many amps came in? So 5 amps came in, 0.5 went that way, 2 went that way. I think you were right. What'd you say? Sorry? 2? Not quite. 2.5. Right? And again, you can use your calculator if you want to, but the nice thing is some of these you can do in your head. I'm fine either way. Okay, and can you put that away? I don't know what you guys are passing around, but I want you focused here. Thank you, sir. Then they all meet up. Evan, let's keep going. 5 amps, you said? Check. Keep going. This is downhill is this way, and I'm saying downhill even though it's to the left, but we're using our imagination, right? We split up right here. How many amps went down this first hill? So how many amps went down this left-hand hill? Must. 3. And is that all the blanks they wanted me to fill in? Good. This is called the current law. It's actually called Kirchhoff's current law, the Russian scientist. He summarized all of circuits with 2 rules. The first one was the rule for currents. He basically said current doesn't vanish, but I'm breaking it down a bit further. What did you do in school today? We went skiing. Oh, let's keep going. Anybody want to try this one? Thomas, let's go skiing. Where's the battery, my friend? Okay, which way is downhill? Let's do that. Okay, guys? Thomas, did they tell me the total number of skiers on the hill, the total current? Oh yeah, this was a little easier. They gave me that. So I always add, coming from the chairlift, coming from the battery, 4.5 amps. Okay. Downhill is this way. I guess we split up right here. Thomas, how many amps went downwards? How many amps went this way? Oh, how many amps in this hill, this resistor? Got to be, because there's no junctions between there and there. Still 1 amp, right? How many amps grand total were we starting out with? So if 1 amp went this way, how many amps went this way? Must. And, oh, how many amps in this resistor? 3.5 amps. And by the way, I'm using generic resistors instead of light bulbs to say this works for any whatever appliance you hook up, okay? How many amps right here at the bottom? Still 3.5. Going which way? Oh, how many amps at the bottom right here? 4.5. All I can do is add more pathways, Mateo, more forks, and I can make it a little trickier, but this is going to be the strategy. Don't panic. Try and find total current, or if they didn't tell you total current, try and find 2 branches where they told you everything, and that must be total current. Oh yeah, turn the page. Then we come to the voltage law. Gesundheit. Then we come to the voltage law. And the voltage law says this: if you walk around a circuit, and by that I mean is if you end up back where you started from, always going downhill, any voltage loss equals voltage gained. Oh, you lose voltage going downhill. You gain voltage going uphill. In terms of my ski hill analogy, Micah, what I'm really saying is this. The VL, the voltage law, says the chairlift takes you up the mountain. The resistors take you back down the mountain. So let's suppose instead of a chairlift, let's suppose this was a 6-volt battery. If this resistor here lost you 4 volts, how many volts would this resistor have to lose you? If you're getting a 6-volt battery, and you lose 4 volts on the first hill, how many volts must you lose on the second hill for this to work? Priya, you're right. 2. Whatever voltage you gain, which is almost always going to be from like a battery, we're not going to look at plugs too much. We're going to look at just nice batteries because it's a little easier. You have to lose that going through the resistors. And this is why I told you about that short circuit. The reason a short circuit is, you don't have the resistors to lose the energy. You have to lose that energy in the wires. How do you lose energy in the wires? You heat them up, fire bad. And that's why when you were doing that circuit sim a couple of weeks ago, some of you got the big fire thing, right? Adrian, you with me? Okay, you stop turning pages, and I want you focused here. Okay? You can wait. So, it says, find the unknown voltages and voltage drops. Matt, let's go skiing. Ready? Don't freak out. I'll walk you through this, my friend. I think I can make this a little bit bigger. There we go. Where's the battery? You see it? Okay, I'm going to call it the chairlift. How high? How many volts? Okay, that means right here, we are 20 volts high. The ski hills are the resistors. Have I gone down a resistor anywhere here yet? Yet. So right now, I'm still 20 volts high. This is like the level path that you take to get to the nearest ski hill once you get off the chairlift. You haven't gone down any of the big hills yet. I know in real life it's a little bit downhill. We'll pretend it's not. Okay? This hill is 8 volts high. How high did you start? You went down an 8-volt hill. What's the voltage measure right there? 12. Does that make sense? Okay. They didn't tell me how high this hill is. They didn't tell me how high this hill is. But I do know that once I finished this hill, I got to the bottom of the chairlift, 0 volts. So how high am I right here? Well, right here, I must be on the ground. So how high must this hill have been? If I was 12 volts here and 0 volts here, what must I lose going through this resistor? Must. 12 volts. Really, William, we're saying what goes up must come down, but it's voltage. Not quite accurate, but it's close enough to solve the circuit. Is that okay? I don't know what you guys are looking for, but I think you can relax and focus on the lesson.
Yeah.
Let's try another one. Okay. Dev, find the battery.
Battery?
Okay, we're on this one. You there? Yes? I'm going to check the notes to see that you're writing this down, of course.
Yeah.
Good. Find this one. Find the battery. Right here?
Yeah.
How high? How many volts? 10. Okay, look up, look up, look up. So right here, how high are we still? We haven't gone down any resistors, so how many volts would we measure right there? 10. Write that down. Okay. Now, downhill is this direction. It's that direction. And it looks like right here we split up. Some people go this way. Some people go this way. Let's just tackle one ski run. So Devante, look up, look up, look up. I can ski downhill by going through that hill and getting back down to the bottom. Right? I went downhill the whole way. How high did you say the voltage gain was? 10. So how high am I above the first hill still? Still 10 volts. How high am I right here? So how high am I right here? Must be 0. Micah, joy of my heart, what did I lose going through that ski hill? How many volts I must have lost? 10 volts. By the way, you could write -10, but we've gotten into the habit, Layla, over time of saying, hey, it's a resistor. You always lose voltage going through a resistor. Just write 10. We clue in it's a loss. Yep. Nope. Nope. Here's what we're saying. These kids got off the chairlift, okay? You guys said, we're going to go down this hill. I said, well, I'm going to go down this hill. But we were able to meet up at the bottom on the ground. The only way we were able to meet up on the ground is, you know what? I must have lost 10 volts. And you know what? You're 10 volts high. You ended up on the ground. How many volts did you lose on your hill? Must have. This is a little strange. People don't understand how circuits work. But it turns out this resistor loses 10 volts. This resistor loses 10 volts. Nope.
There's two different.
But the skiers got to go down. Got to go downhill though. So if it was 5 and 5, what you'd be saying is the skiers went down this hill and somehow climbed back up this. No. We're going downhill. Current only flows downhill. So either I can get back to the bottom of the chairlift by going on the right-hand resistor, which means I start at 10 volts, I end at 0 volts. I have to lose 10 volts, or I can get back to the bottom of the chairlift by ignoring that, going down the middle resistor, starting 10 volts, end at 0 volts, must lose 10 volts. I know, it's a little tricky. Hey, let's try another one. Okay? Let's try another one. Rebecca, you want to go skiing? Let's go skiing. By the way, voltage is a little trickier, so we'll spend more time on it. First thing, Rebecca, see the battery? How high? How many volts? Which way is downhill? Okay, let's put a little yoink. How many volts high am I right here still? 12 volts. So, Lydia, in our analogy, all the skiers, all the current goes through this first resistor. How many volts is this first resistor? So, right here, how high is everybody? How many volts? We gain 12. We lose 8 going through here. So we don't add, right? When we go through resistor, we lose voltage. 4. Yep. Oh, you're giving me the answer. So what we're saying is, right here, we all come to a stop. There's a fork in the ski hill. We shake hands. Some people go this way. Some people go this way. But the fact that we're able to shake hands here and all of us meet up here, it must mean if we're skiing, Lydia, that we went through the same height drop. Whatever ski hill you skied down must be the same height as the one that I skied down, same voltage. Why? Because we shook hands at the top and we met up at the bottom. Otherwise, there would have had to be another chairlift or something to change the height. So how many volts high did you say, William?
4.
So right here, we're 4 volts. How many volts are we at the very bottom right here?
0.
So how many volts did we lose going through this middle resistor?
4.
Yep. Or some of the current went this way. How many volts high were we when we shook hands? Still 4, because we haven't got on any hills yet. We went down one hill and got to 0 volts. You know what? This hill must also have been 4 volts.
I think I was confused because in amps they split. But
Yep, current splits, voltage does not. Voltage is height, not skiers. Okay? Do ya? Can I throw an ask you? Let's try the next one, you and I. Okay? Let's board. See the battery? Okay. How high in the top left corner still? 60. Okay. Everyone goes down this hill. So everybody loses 15 volts. The entire current loses 15 volts. How many volts high are we right here then? Well, so 45 there and 45 there. Cool. Let's go down the middle hill. How high is that one big middle hill? It tells us. So how many volts do we lose? 18. So how high are we when we get to the bottom? Whatever 45 take away 18 is, which is what? 27? And again, in your head or calculator, 27? Let's keep skiing, William. Which way is downhill when we get to here? To the right or to the left?
To the right. Or left.
Left. Okay, right here, we're still 27 volts high. How high are we right here? How high are we right here? So what must we have lost going through this resistor? Must have. If you put a voltmeter across that resistor, it would register 27 volts. Lydia, I think this will actually answer your question better. You ready? How many volts from here to here? How many volts from here to here? How many volts from here to here? How many from here to here? Since we were able to shake hands and meet up, these two hills better add to 18. They have to. How big is this hill? 10. How big is this hill? It's going to be 8. Let's walk through it, but it's going to be 45, take away 10, 35, take away, I don't know, but how high were we when we met? 27. So this better be 27 volts, which means that's got to be 8 volts. This is the voltage rule. It says what goes up must come down. Okay? And I agree, Lindsay, it is trickier than the current rule. But actually, this is why you can plug in 2 appliances from one outlet. Each of those appliances is getting 120 volts. There's your first appliance. Hey, this is an extension cord with 2 prongs on it. That also would add up to, in this case, 18 volts, but from a household plug, 120 volts apiece. This is too much writing. For what it's worth, although it's helpful at first to label the voltages everywhere, what we're going to start to do, Mohammed, is we're only going to label the voltage gains from the chairlift, and we're going to label the voltage drop in each resistor. We're not going to label above each hill and below each hill. It gets too cluttered. So in all of the following examples, if I write a voltage next to a resistor, Adrian, that's negative. You're losing voltage because you're going through a resistor. If I write a voltage next to a battery, you're gaining voltage because that's what a battery does. Is that okay? Okay. Rebecca, we never did finish yours properly, did we? I started skiing and I never finished. Let's go skiing, you and I. Okay? It says, find the unknown voltage drops, currents, and resistances. Now we're going to put it all together. And we're going to finish, I think, with this example. This class goes to 135?
Yeah.
So we're going to finish with this example here. Start on the chairlift. How many volts high? Let's put a little arrow pointing downhill. And the other thing I want to find is total current. Folks, let's look at this circuit. Can you tell me the total current from anywhere here? Let's see.
No.
Start walking. Have we hit any junctions yet?
No.
Have we hit any junctions yet? Do I know I have? There was a junction here somewhere, different wires breaking off? So this is the first ski hill, but it looks like everyone goes down this hill. How many amps in this hill? How many amps in this hill? 4 amps in this hill. So how many amps must have left the chairlift? Must have left 4 amps. Let's put a little 4 amps, well, right there. The total current here is 4 amps. Okay. How many amps went downwards? 3, Mohammed? Yes? How many amps went to the right then? 1, so we can fill that in. There's 1 amp going through that resistor. So far, so good? Let's see what we can do for voltages. How high was the chairlift? How many volts? 18? How many volts does everybody lose going down, William, this hill here? 6. What's left? 12. Now I notice some people go this way and they get to the bottom. This is the only other hill they go down, so how many volts must there be in that hill? How many volts must they lose through that hill? Must lose 12. Some skiers go this way and they go down this hill and get to the bottom. How many volts must they lose? Must lose 12. And the last thing we're going to find is each resistance. From your pink sheet, if you know V and if you know I, can you find R?
Oh, yeah.
Yeah, how? Okay, find what's the top resistor then? V over R? V over A? I don't think 6. Okay, we're going to pause here. We'll pick up with this next class. Your official homework is, folks, please make sure that you get this done. I'd like to mark this next class.